All right, now we're going to transition in this book. We're going to do a series of topics related to physics. So this is good for you physics engineering majors. You're going to see these topics again. So the first topic is this idea of work. Work is, as a physics concept, is defined as force times the distance against the force. For example, when you lift a book, let's say you have a 5-pound calculus book and you lift it vertically. Notice vertically is against gravity, right? You're moving it the opposite direction of gravity. So you have to do some work, so to speak, to lift that book. But literally, work is defined to be 5 pounds, and let's say you lift it 2 feet. That's the distance. 5 times 2 is 10 foot-pounds of work, we would say, you have done. Okay. Or, okay, so we have to get comfortable. If you've taken physics, you're aware of this, or maybe chemistry. If you haven't, in the US, units for force are in pounds, and distance is usually measured in feet. This is also called imperial units. Most of the world uses the metric system. And so running a problem in the metric system, in the metric system, our unit of force is newtons. I'm going to skip down here. A newton, just for comparison, is about 1/4 of a pound. So let's say you took 100 Newton, and we just use N for newtons, chair, so that would be about 25 pounds, and you lift it 2 meters. 1 meter is roughly 3 feet, so maybe about 6 feet. Then you will have done 100 times 2, 200 Newton meters. When we multiply it, we just read that as Newton meters of work. Now in the metric system, Newton meters is given a name for a physicist. So we call that joules, Joules. So 200 Newton meters is 200 joules of work. And that's kind of what I'm describing right here. Newton meters is joules. So we're going to do a lot of stuff with work, but let's start by talking about springs. If you've ever stretched a spring, and I think of the springs like the metal ones and stuff like that, but a spring can even be thought of as a rubber band, has the same property as a spring in that the force required to stretch that spring further and further, it gets harder and harder to pull and stretch that, right? And that would be similar with a spring. So the force required to stretch a spring is proportional to the distance that you stretch it. The further you stretch it, here's a smaller rubber band, it's going to require more force to stretch that thing further and further. So force is proportional to the displacement. So there's a constant of proportionality. We'll say F is equal to kx. That's a very common, familiar rule if you've taken physics. This is called Hooke's law. So that says the force required to hold a spring a certain distance, it's proportional to the distance. And K is usually referred to as the spring constant. It's different. It kind of measures how sturdy the spring is. Here's a very thin rubber band. It's pretty easy to stretch this thing pretty far. So the spring constant would be pretty small. Whereas this smaller, thicker rubber band, it's hard to pull that very far, so that would have a higher spring constant. Okay, so an example here. Let's say it takes 20 newtons of force required to stretch a spring from its natural length of 5 meters. Okay, that's a very long spring. Natural length, let's just pretend these springs are hanging, okay? And let's say just from its own weight, it hangs 5 meters. And you want to stretch it out 7 meters, which means your total displacement is really only 2 meters. You're really only stretching it 2 meters. And it takes 20 newtons of force to do that. So if F equals kx, again, my displacement is the difference from how far I stretch it minus its natural length. So that's 2 meters. 20 newtons of force equals K times 2 meters. I can solve for K and get 10 newtons per meter would be the spring constant for that particular spring. So then another question I might want to know is how much work was done when I stretched that spring from 5 meters to 7 meters. Okay, and unlike the book example, when we said we were lifting the book or the chair, you can't just multiply 20 newtons times 2 meters to get 40 joules of work. And why? Unlike when you're lifting a book or a chair, what requires the same amount of force, however far you lift it, the spring force changes. As the longer you stretch that thing, the force is going to get higher and higher. Okay, so if the force is constantly changing, you can't just multiply force times distance. Instead, we're going to need an integral to calculate the total amount of work. So here's how we do this. We're going to set up a system here. Let's define x equals 0 because is the natural length of the spring, which is 5 meters. Okay, we're going to call that x equals 0. And we're going to imagine stretching this spring in little tiny increments. Okay. And so let's imagine we have x meters out from its natural length. So the force required to just pull that string x meters we know is k times x. So F is equal to k times x. And then we're going to imagine moving that just a little tiny distance dx. So my work is force times distance kx times dx. And then just imagine we're pulling it little tiny bits at a time, each increment of dx, and our integral is going to add up all of those little tiny increments from 0 to 2. So we can then set up the integral kx dx. We figured out k in part A was 10, and we're going to integrate that from 0 to 2. And we end up coming up with a final answer of 20 Newton meters, which we can call 20 joules of work. Now, what if we were to stretch that spring 2 more meters, 2 additional meters, from 7 to 9 meters? You might say as a gut reaction, well, that's still 2 meters, so it should be the same. It should be 20 joules of work. But then if you think about it, the force is going to be even stronger, right? To pull that from 7 to 9, the force is going to get greater. So it seems like it should be more work, and it is. So we have the same integral. This time we're going to integrate from 2 to 4. That was 2 corresponds to 7 meters, 4 corresponds to 9 meters. And it's the same integral, but this time you get 60 joules of work. And as expected, that's more because the spring is harder to stretch as you pull it further. One more example. So let's say we have a 50-foot cable that weighs 100 pounds, and we're going to use that to lift an elevator that weighs 1,000 pounds. And we want to calculate the work required to pull both the cable and the elevator the entire 50 feet. Okay. So the thing we have to, this is a good like engineering problem because we have to consider both the elevator and the cable. Both of those require work to lift up. And so if we neglect one of them, we might get an underestimate of how much work is actually required. And we're going to think of this as 2 parts. There's the work required to lift the elevator, and that's a constant force. The elevator always weighs 1,000 pounds. So you can just multiply 1,000 pounds times 50 feet gives you 50,000 foot-pounds of work just to lift the elevator. The cable, however, gets lighter. As we move this elevator up, you have less of the 50-foot cable that weighs 100 pounds that's hanging, which means it's getting lighter. So the force required to lift the cable varies. And so just like the rubber band, it's kind of the opposite of the rubber band or the spring, right? The further you stretch it, it gets a harder force. Well, I guess it's the same thing. As you bring it in, it's less and less force, right? As you bring it in, just like the cable. But bottom line is, since that force varies, we're going to need an integral. Okay, one of the challenges I think of these types of problems is you have to kind of set up your own coordinate system. Most of the time, nobody does it for you. So there's a couple of different ways. You could set x equals 0 to be the top, where when the elevator is up at the top here, and then 50 down below. You could also do it the other way. You could decide this is x equals 0 and this is x equals 50. You would have to adjust your integral. We'll talk more about that as we do more work integrals in a future video here. But for now, let's define x equals 0, because that means there's 0 feet of cable out, right, to be up at the top, and 50 feet of cable at the bottom. Okay. The trick, we can think of the cable as kind of like a spring in that it has a, if the cable weighs 100 pounds and it's 50 feet long, then it weighs 2 pounds per foot, right? 100 divided by 50 is 2 pounds. Each foot weighs 2 pounds. And we can kind of think of that as like K. So for example, when all 50 feet of cable are out, the cable weighs 2 pounds per foot times 50 feet is 100 pounds. But when there is, say, 30 feet of cable out, the cable weighs 2 pounds per foot times 30 feet, which is only 60 pounds. Okay. So same idea as the spring. Let me slide this back up. When there's X feet of cable out, the cable weighs K times X, which is going to be 2 times X. And we're going to imagine moving it just a tiny distance, dx is our distance. And we're going to add up all of those little movements from x equals 0 to x equals 50, 2x dx. It's a very simple integral, x squared. From 50 to 0 gives you an additional 2,500 foot-pounds of work. So the total work required to lift the elevator and the cable is the 50,000 plus the 2,500, 52,500 foot-pounds. And again, just a note, especially for your engineering majors, right? Plenty of engineering disasters have happened from engineers neglecting to account for things, right? Yes, the majority of the work is in lifting the elevator, but if you did not include the work required to lift the cable, it's 2,500 foot-pounds. I mean, that maybe is not insignificant, right? In a certain situation, we might exceed, right? We have to account for everything, all of the work that would be required here. So anyhow, we'll do some more work examples in the next video.